This is a short lesson on the equations of motion, and it all starts off with the fact that acceleration is constant. So everything we're going to talk about here is only valid when acceleration is constant. And of course, when we make a graph of velocity versus time, that will show up as a constant slope, because remember the derivative, which is the slope, of the velocity versus time graph is acceleration. All right, so let's start off with the definition of acceleration. It is the change in velocity over the change in time. So my final velocity minus my initial velocity is my change in velocity divided by time. If I cross multiply the time to the other side, I get AT equals VF minus VI, and then I solve that equation for VF equals VI plus AT. That is my first equation of motion. And if you think about what that is saying, it's quite logical. It's saying that my final velocity is equal to my initial velocity plus the change in my velocity. So if I have a positive acceleration, this will be a positive number. I'll be speeding up, and my final velocity will be greater than my initial velocity. And if the acceleration is negative, if I'm going in the positive direction, I will slow down, and my change in velocity will be negative, and my final velocity will be less than my initial velocity. And if I look at the units of acceleration times time, acceleration has units of meters per second squared, time has units of seconds. So when I multiply it together, I get meters per second. So everything over here agrees. Meters per second equals meters per second plus meters per second. Okay, let's look at another example. The definition of average velocity is displacement divided by time, so we'll rearrange that to say displacement is equal to average velocity times time. Now here's where we see that this is only valid for constant acceleration, because my average velocity is the average of the initial and the final velocity values. That will only be true if this is a straight line. So my average velocity can be calculated by taking my initial velocity and my final velocity, adding them together and divide by 2. And then I can just rewrite that displacement is 1/2 VI plus VF times time. All right, so let's use the first and second equations of motion that we just came up with to come up with a third equation of motion. So what we'll do is we'll take our first equation that we came up with and we'll substitute into the second equation where we see VF. We'll replace it with what it is equal to, VI plus AT. So in this part of the equation, you'll see I've substituted VI plus AT in for VF. And when I multiply the T through the parentheses, I get this. And when I multiply the 1/2 through the parentheses, I come up with my third equation of motion that says displacement is equal to initial velocity times time plus 1/2 AT squared. Let's also look at a graphical analysis and come up with this equation in a different way, using a graphical analysis. So here is a velocity versus time graph. The slope is constant because these are only valid for constant acceleration. And the acceleration, of course, the slope is delta V over delta T. And I've changed it so that we begin at some velocity, not at a velocity of 0, but some initial velocity at time t equals 0. Just analyzing this from a graphical standpoint, a straight line on a graph is y equals mx plus b. Y is a function of x. So x is my time. So x is time. The slope of the graph, m, is the acceleration. My y-intercept is my initial velocity, and my function of x, which we call y usually, is my whatever value I get on the red curve at some time t. So that's my final velocity. I also know that displacement is the area under the velocity versus time graph. And if I look at this graph, that would be the sum of area 1, this rectangle shaded with cross-hatching to the right, and area number 2 cross-hatching to the left. So the area of this rectangle is base times height. The height is V initial. The base is time. So the area of that region, A1, is VI times T. And then the area of A2, it's a triangle. So 1/2 base times height, where my base is T. My height is from VI to VF. So VF minus VI is my height. And so the area of that triangle then is 1/2 VF minus VI times T. Now, if I take this equation over here and rearrange it for V final, I'll substitute in, if I take V final minus V initial is equal to acceleration times time, I can replace this V final minus V initial with acceleration times time, and that multiplies by this T to give me 1/2 AT squared. So my equation of motion agrees using a graphical. It agrees with our previous equation using a substitution method. Here we've used a graphical method to come up with the equation a different way. And lastly, let's take these two equations. I'm going to rearrange them a little bit. This one on the left, I'll square both sides and expand the squared term. And this equation, I'll multiply both sides by 2a. And so this becomes this equation here. And I see that this part of the equation on the right is the same as this part of the equation on the left. So I'll replace all of this with 2ad to come up with my fourth equation of motion. Vf squared equals V initial squared plus 2ad. If you'll notice, each of those equations had only 4 variables in them, but there are 5 variables overall. Displacement, V initial, V final, acceleration, and time. Just a little reminder here that we can only use them when acceleration is constant. And if we look at all the equations at once, we see that even though there are 5 variables, each equation only has 4 variables. So any equation, if you know 3 of these 5 variables, you can pick an equation that has those 3 and solve for the 4th. And once you know the 4th, you can pick another one. In other words, you only need to know 3 of these 5, and that will allow you to solve for all 5.